So hello everyone, welcome to Whitepaper Session. My name is and today I am presenting my white paper on the topic optimizing ambulance positioning for faster emergency response. I will be mainly focusing on the topic ambulance dynamic realization problems. So in emergency response, the emergency response time is a very critical factor in saving lives. Even a few minutes of delay can kind of drastically change the patient's outcome, right? So this work kind of explores how a biologically inspired algorithm helps in the allocation and reallocation of an ambulance position in a city map. So the core problem is that emergency calls are totally unpredictable. Suppose there is an ambulance and it dispatches an emergency call. So when it dispatches, it often leaves behind a region that is uncovered. So ADRP, which is ambulance dynamic realization problem. So ADRP focuses on repositioning the available ambulances in real time so that each and every region in the city is covered. So the goal is very simple. I want to minimize the reaction time, my reaction of the ambulances. I want to minimize the reaction time such that while maintaining the optimal coverage in a city. How do I do that? We must look into what is currently being done. Currently, most emergency medical services rely on static infrastructure. There are mainly three problems with that. First is static infrastructure. Second is centralized dispatch systems. And the third is traditional optimization models. The problem with traditional optimization models is that they are computationally very expensive. Although they are mathematically very sound, but the computation requires a lot of power. And due to this, these models are not very scalable on large cities. So I want a solution that is affordable, that is scalable, and that is adaptive. So to tackle these three problems, I want to propose a solution that using slime mold algorithm. What is this algorithm? This is based on an organism that is called slime mold. So this is a very fascinating organism. This forms a very efficient net. First of all, this organism does not have any brain. Also, this forms a very efficient network while finding its food. How does it do it? So this basically explores multiple paths and it reinforces the most efficient ones. So this emergent nature of this organism kind of makes it very brilliant motivation for optimizing network problems such as ADRP in our case. So you can see this is the slime mold algorithm. This is the slime organism. So how do we code this? In slime mold algorithm, we kind of depict every possible solution as an agent, and every agent moves through the search space. In our use case, this search space would be a city map, right? So when an agent moves, its position is determined by mainly two things. First of all, I want to know what is the current best solution, and the position is also influenced by other agents around it. Over time, any agent continuously updates its position, and finally it settles down and converges to an optimal or near optimal solution. To visualize this concept, we can simulate this slime mold behavior, and the simulation runs through the following steps. We must initialize all the agents randomly. We place the emergency demand points. Agents move while sensing other trains. Trains from other agents. Agents also deposit their own trains while movement, and the trains diffuse and evaporate. You can see the agents are leaving a trail. They are also bouncing off the boundaries. The trails are getting diffused. The trails are also getting evaporated there. Two agents sensing the trails from each other. And here multiple agents are forming a pattern, and there is an attraction point to which all the agents are getting attracted. This is a demonstration video with 100,000 agents all following the same set of simple rules. As you can see, all the agents started off randomly, but slowly and steadily they are forming a beautiful pattern. But how do we implement this into our use case? Before using the slide available, we must introduce a few more features, such as we must be able to ingest a map on which our simulation should run. We should also be able to generate a heat map to differentiate the high density trails from low density trails. On high density trails, we will intuitively place the ambulances, and we should also be able to check the response, if the response is dynamic or not. And finally, we should track the frame rates per second to evaluate if my simulation is working properly or not. This is the simulation after we have implemented all the core features. As you can see, in the red scores, the heat maps are getting generated. Using my curve, I can also block some paths and see how the simulation reacts. Now there is a new heat map over there on the top. I will be blocking that also to see how the system reacts. Finally, I am also tracking the FPS. So as you can see, the simulation is currently running at 36 or 37 frames per second. But this is, if you can see that the simulation is running with 50,000 agents, and this is a very small region. So if you want to scale this for a larger city, how do we do that? So the bottleneck that is that there is a lot of calculations being done for every agent, and due to that, if you use a large number of agents, our CPU kind of shows, because yes. So as you can see, there is a complexity of big of n to the power 4. So if I want to scale it to a large city, we will need kind of somewhere about 10 million to 100 million agents, and for that many calculations, our CPU is just not capable of doing that. And even if we try to do it, our system will just choke and it will kind of run at 1 or 2 FPS. That is not acceptable. So what do we do? Luckily, we can exploit the parallel computation of GPU, and the operations like agent updates and grid operations are just very suitable for parallel computation because they just use many nested loops. So nested loops are very suitable for GPU acceleration. This is a simulation running on GPU. As you can see, as a fact, I can tell you that this is running for like 10 million agents, and you can see the FPS is 144. Previously, it was 50,000 agents on CPU, and the simulation was at 37 FPS, and this is 10 million agents with 144 FPS. You can see the comparison. As the number of agents increase, the CPU chokes down, but GPU consistently performs better than CPU. 10 million. CPU does not even run. So concluding my project, we can safely say that ADRP is essential for efficient coverage of an area, and this bio-inspired algorithm is also helps very effectively in ADRP, in the solution of ADRP, and this by combining the CPU and GPU, by combining the GPU, we can scale this for a larger map. Now, thank you for your attention. Now, I would like to invite Devraj for his presentation.
Hello. Okay, so hello everyone. My name is Devraj and today I am going to present my project Artifact, which is a memory optimized AI pipeline for image exploration. So first of all, what is Artifact? First you can see the demonstration. I input a damaged historic image and it gives out a clean restored image. So that's what we are doing here in this project. Let's take an overview. So we have quite a number of historic images which are degraded, damaged, uniform. So what I thought of is, let's just make a deep learning model which restores all the damaged images so that they can put up in museums and everywhere and they can be studied thoroughly. That's what my problem statement was, and I designed my model Artifact. This is the complete workflow. First, we prepare a data set, then we train a unit model for the pixel and color restoration, and finally we pass it for restoration pipeline. Let's look into it in detail. Okay, so first problem which I faced was anywhere on the internet you cannot find paired data set. In supervised learning we must have a paired data set, right? First will be a damaged image and second will be a restored image. I could only find some 200 or 300 paired images which were fine for training, but I don't think, and even you must be knowing that only 2 to 300 images doesn't matter in deep learning. So what I did was I took some 8,000 plus images, 8,000 plus clean images, okay, and I applied synthetic degradation using mathematical concepts like desaturation and generated random tracks and edges everywhere. So that way I generated a paired data set of about 8,000 plus images, and I used that for training my model. Let's come to the training part. So what I use is a unit model. So first of all, what is a unit model? We can see any image, but the computer cannot see, right? So what a unit model does is it breaks down the images into certain mathematical values which the computer can see. Like we can imagine this board. You are seeing that it is a rectangle, but the computer doesn't know, right? So it breaks down its first triangles, then the edges, then the particular color for each pixel. That way we train a model. It goes through the depth. You can imagine it like a YouTube first. It encodes for the computer what the computer must see, how the computer sees an image. Then at the bottom of the YouTube, it trains and calculates all the losses. and finally the decoder comes into action, the right part of the YouTube, and we get the final result. Okay. Also, we are using two losses here. First is L1 loss for each pixel. So it compares the input damaged image and the actual restored image which it should return, and it calculates loss for each pixel. Just the absolute value, we are not squaring it because it will increase the loss by much extent. And one more loss I have taken here is VGG19. So you can understand VGG19 as a master painter, which comments on like you can do this, you can do that. Like suppose a trained painter like Da Vinci or Picasso, something like that. So we are taking two losses here to train a model. Now the inference pipeline. Before we pass our damage into a model, we first start it into 512 into 512 pixel tiles, and then we pass it through a Llama. Llama is a structural inpainter which paints all the cracks and edges which I was talking about. It hallucinates and fills in all the gaps. Then we pass it through a unit model which restores the color and everything which I was talking about. Then we pass it through a GAN. GAN stands for Generative Adversarial Networks. Let's not go into that much detail right now. What a GAN does is it upscales our image to suppose 4x to 10x resolution because our unit model hallucinates. So it will produce blurred images. So we pass it through a GAN so that it just upscales our image and makes it more sharp. Then we pass it through a GFT GAN. What a GFT GAN does is suppose most of the paintings you will see that there are faces on some man or some anything like that. So it enhances all the facial structures like eyes, mouth, nose, everything. Okay. And finally we average out all the extreme reds and extreme blues because you must be knowing that any pixel is denoted by three values RGB. So if any extreme red value is there or any extreme blue value is there, it averages out everything and finally we get a restored result. Let's have a look at that. Yeah, so first we get our input damaged image, then we pass it through Llama which fills in all the cracks and edges. Then we pass it through a unit model which restores all the color. Then real PSCR GAN, it upscales the texture. Then GFT can restore the face. And finally by averaging out all the values, we get a final. So there is a video demonstration which you can see. Okay, so one more example you can see. Yeah, second problem which I faced is I have a consumer grade device with only 6 GB of RAM. So our model demands more than that, and we cannot run that on our domestic devices. Like, okay, you understand that. So what I did was, first of all, I used tile technique. I divided my image into certain number of tiles. Okay, imagine let's say suppose 5 multiplied by 5 tiles, and each tile is processed independently, so that there is no overloading on our GPU and everything is processed fine. One more optimization technique I used was that I divided my pipeline into certain models. First my unit rate model, then my first GAN, then second GAN. So what it does is, what optimization it does is, it does not overload the GPU. First my unit model performs, then I clear the session. Then I use my first GAN, then I clear the session. That way there is no overloading on our GPU and everything works fine. What future prospects I see in this project is that first, instead of Llama which just uses math, simple math, we can use generative diffusion and we can use some pre-trained AI model to fill in all the cracks. Secondly, we can use style level fine tuning, like we can use neural strength transfer like from Da Vinci or Picasso class or any famous thing they can think of, so that it analyzes which painter has made it and we restore that. These are some references which I used, especially for GANs and VGG90. Okay, so thank you for the presentation. Now, next question. Hello, everyone. So, hello everyone. My name is Keshav Bharati, and today I will be talking about agent-based simulation models, mostly on voice talking simulation and natural selection simulation. So, let's try it. So, what are agent-based simulation models? These are autonomous agents which follow simple rules and locally interact with its nearby neighbors. This forms complex patterns and emergent behaviors. Few examples of these are flocking birds, pack systems, predator prey ecosystems, and economic markets. So the question arises: why use agent-based models? Well, there are a few advantages for it. Those are: it helps us study complex systems, observe how patterns are formed, and simulate real-life phenomena. So there are a lot of applications such as biology, ecology, computer graphics, and games, and much more. So, the first simulation which I will be talking about is voice talking simulation. So, this was discovered and introduced by Craig Reynolds in 1986. It has a lot of applications such as computer animation, game development, robotics research, and cloud simulation. So, what are voids? Voids or void objects are autonomous agents which are used to model a school of fishes or a flock of birds. While voids are a group of agents, each void is an individual entity which has its own position and movement. Now, since there is no central coordinator in a flock, this helps us in forming complex behavior when there are multiple points. So, each void has its own position, velocity, and local awareness, which helps us in detecting nearby. Voids follow the rules in specific. Those are separation, alignment, and cohesion. Separation is basically that when two voids come very close to each other, they tend to move apart. Alignment is that when voids tend to move in the same direction as those of its nearby neighbors and try to match the velocity. And finally, cohesion, which is that a group of voids tend to move to the center, and try to scale the flow. So, first, I'll show you guys what happens when these are separate, when only separate rules exist, and what happens when we confine all of them. So, this is what happens when there is just alignment. As you can see, they interact a bit with each other and we don't try to move in the same direction. It is very messy and they don't have any brain or anything. Just move back. Next is cohesion, and as you can see, they all try to move in the same direction and try to move towards the center. And finally,
finally, separation, where when two points come together, they tend to go apart. Yeah. So combining all these three, we get what are known as circles. Yeah. So as you can see, alone they don't have any play, and with a single rule they don't do much. But combined, they move in very complex behaviors and it is. So yeah, the next thing which I'll be talking on is manual selection. This was inspired by Darwin, and it helps us in demonstrating how populations change and evolve over time. So there are a few key points which are needed for this. One is individual variation, which is that different traits are affect survival and reproduction. Survival advantage, where based on a particular trait, you have a good chance to survive in a particular ecosystem. Inherited success, which is that children take over traits from their parents. Population adaptation, which is states that over time the population adapts to its ecosystem. And finally, ecosystem, which is that different ecosystems, different traits are better compared to others. And this helps us, and this causes the traits to be other. So, in the current ecosystem which I will be talking about, there are three things. First, the predators, prey, and food. Predator's job is to hunt down prey to gain energy and to reproduce. While prey's job is to gain both energy from eating food and also avoiding predators. And finally, so in this way, nature interact, competes, and evolve over time. So, what are all the traits in the current situation which I'll be talking? One is speed, which is basically how fast the agent can move. So, the faster the agent moves, it's better, but also it has a cost since moving faster also consumes more energy. Similarly, for sense, it helps us basically senses the radius, or you could say the amount of area a particular can cover, and check for food, prey, and predator. And finally, energy, which is the resource which is needed for survival and reproduction. So, what exactly happens? The first, prey and predators, they gain energy and also survive by avoiding each other. And once they accumulate a certain amount of energy, they reproduce when they get sufficient energy. And finally, those children which are born get their traits from their parents. This results in evolution over generation, and successful traits become more dominant. So, how do they move? Well, in this simulation, I use something known as water algorithm, which helps us in producing smooth movement. So, what it does is, for a particular agent, it takes a circle from some distance away from it, and on that circle, it takes a random spot. And in that particular frame, the agent will try to move forward. Now, since this is done each and every frame, this helps us in creating random and smooth motion. So this is the formula basically, which is very simple, but V is the velocity, current velocity, and direction. A is the shearing constant, which helps us in moving, and D is the distance from the correct position to the circle which we are taking, and D is the direction, and T is the point on the circle, and B max is the maximum velocity which a particular agent can have. So this is how it goes. Yeah, so it's smooth and it moves back. So how does it work? Well, this is the most important thing to say, which is that total energy works based on this formula, and each and every frame it increases based on its speed and its size. So in the correct simulation, the place will be triangles, and when it's green in color, it means it has found a food. When it's blue, it's just wandering randomly, and when it's red, it means that there's a predator nearby and it's kind of over. For predators, they are squares, and when it's blue, they are wandering randomly. When it's red, it means they have found a prey and tried to catch it and eat it. And finally, food are circles. So I'm showing you a few demonstrations and based on the ecosystem different. So in the first two, there will be only what we say just prey and food, and the food is more. So what you can see is like speed is more dominant here. Since the faster you are, the more chance you have of getting food compared to others. Next, when you have less food, it's more necessary to have a larger sense radius since you can detect food faster and eat it. And if you don't, you just die. And combining this with predators, you get some really cool stuff. So red is squares are predators, triangles are prey. As you can see, when they eat a sufficient amount of food, they reproduce. So finally, I'm discussing about future optimization which should be done. One is parallel processing, where multiple agents can be updated using multiple CPU cores or GPUs, which helps us in speeding up the process. And this helps us in reducing the overall time complexity and time required. And next is spatial quantum, which is basically we distribute the whole ecosystem into small cells and regions. So, and based on the particular region in which the agent is, it only has to interact with the nearby cells, and it only takes the agents in the nearby cells instead of checking the whole ecosystem. So this helps us in reducing the time complexity from warp and square to warp. So and which helps us greatly. So yeah, that's it. Thank you. You guys have yeah, okay, good.
Hello everyone, my name is Shivan and I will be today showing you how I made my Collegian fluid solution. So this is basically going to be a presentation of all the mathematical ideas behind this simulation. So let's start with a practical example. Suppose I give you a square in which there is water or any other fluid, and I give you the velocity of water at each point at equal to 0. So this is basically an example. At equal to 0, suppose the u is basically the horizontal velocity and v is the vertical velocity. So suppose this is the velocity field initial at equal to 0, and I ask you what would be the velocity look like at equal to say 3 seconds or 4 seconds or whatever. How would you solve it? So you would solve that using the previous Stokes equation. So basically that is basically f is equal to ma for fluids. For like infinitesimally small elements of the fluid, you can derive the equation. So it's easily solvable using the previous Stokes equation. But suppose now I give you a more challenging field. Suppose a very complicated field, and I ask you what would be the velocity profile at 3 equal to 3 seconds or whatever. So that is very difficult to solve using analytical methods, like solving exactly using algebra and differential equation. So now we would have to switch to numerical methods. So numerically we have to solve this equation, which is this. Basically this is f is equal to f for fluids. This is the previous Stokes equation for invertible flow. The first one think out what do we actually want to simulate. We want to simulate something. We want to simulate a fluid which is incompressible. What does that mean? It means that the rho is constant. Its density is going to be constant, and the velocity field is going to have x, y, and t components, no z components. So it's only 2D as for now. We are going to keep it simple. And another point that we are going to only keep we will only want to only keep the physics such that it makes it look real. We don't want it to be exactly physically accurate because it would require much more computation. So we would just care about visual plausibility and not physical perfection. So there are two ways, mainly two ways. There can be many ways to, like if you combine those. But there are two core ways to simulate fluids in computers. So one is the Lagrangian and another is the Eulerian method. So the Lagrangian method is basically based on the idea that the fluid is composed of small particles. And like if you take so many, like thousands of small particles, it may give you the impression that it's a fluid. And the another method which we are going to do today is the Eulerian method. In that we take like a grid, and each grid has a like constant property like pressure, velocity, density, temperature, and we are going to apply those equations to simulate the time evolution. So let's talk about the significance of the incompressibility. What does it actually mean? So it turns out that the liquids are very incompressible. They have extremely low compressibility. So we are like going to take it as an approximation as like it has zero. It has exactly zero. We model it as perfectly compressible. And so that means the velocities. That means that the amount of fluid going inside the cell and the amount of liquid going outside the cell is exactly equal. That means like from there it comes that del dot U. So it turns out that since we have like finitely sized grids and not infinitely small like elements, like unlike in real fluids. So because it would require infinite computation. So that's why it actually turns out that we get artificial viscosity out of it due to some Taylor expansion which I will show later. So we get some artificial viscosity, which is a very huge challenge, even if like we don't add our like own velocity. It turns out that artificial viscosity is introduced into the system. So we drop the natural viscosity term anyway, keep things as common. And let's talk about the grid we are going to use for this simulation. So there are many options for the grids. One most simplest option you could think of is that you have a grid at the center, you store the pressure values, velocity values, density values, and center. U and V. That grid is fine, but there's a much better grid for our purpose. We have this grid where the pressure and densities are at the center, but the horizontal velocities are stored at the vertical line. And the vertical velocities are stored on the horizontal lines. So that helps us calculating the divergence very much, as we will see later. You easily calculate the amount of fluid, net amount of fluid minus out. Very easy. V2 minus V1 plus U2. Since we will be solving this PDE numerical, and it's a huge PDE, and it's very challenging to like solve it in a single step. So for our convenience, we are going to divide it into 3 parts and 3 steps, and we will update like step by step to step. So the first step is actually called head. Move everything along the floor, and we are going to use a semi-Lagrangian which is traced back in this way. This will be seen later. And the second step is like body force, which is a simple step, it's just one equation. Simple convert solution. The third step is project. We are going to solve for the pressure such that it satisfies the incompressibility constraint. So the semi-Lagrangian method. The key idea is if we want to find the value of some property at a certain point, we will find the velocity at that point. We will trace back a time step and find the property and particles, we are assuming that there was some particle which came back, which was having some density, whatever, some property, and it like in a time structure it came there, right? And one of the most biggest advantages it has that it is unconditionally stable, unlike other methods. One big disadvantage of this method is that it introduces artificial viscosity, as I told earlier. So this, like it introduces, due to some Taylor series expansion, you could notice that it has some higher order terms, such as the second order term, and the second order term introduces viscosity. So that viscosity term U times delta x. So that is the viscosity coefficient, and it says that if we take a very huge delta x, we get a higher viscosity, and if we take like a high resolution grid, which means a low delta x, that would mean low viscosity and more perfect what we are trying to do. But lower delta x, we would need many grids and much more computation power. So that's a problem of this method. And there are some partial fixes. So some things we can do like compensate for this effect. We could add some velocity. This is called vorticity confinement. So this is called artificially amplified vortices to compensate for numerical damage. So this is another artificial amplification of the velocities so that it cancels out the artificial damping so that it cancels out and we get a non-viscous current. And there are other options like smaller delta x which would be very computation. And this is the last most important step. This is the pressure projection. We would solve for the pressure such that it satisfies the incompressibility constraint. So first we would calculate the divergence, which is very simple. U I plus half minus U I plus half plus U I plus half minus dU. And then we would solve for the pressure. It turns out from the Navier-Stokes equation that pressure satisfies this relation. This is called a Poisson relation. Right, so we would solve for that pressure and then we would apply that pressure gradient onto the velocity so that it satisfies the velocity, so that the velocities are not incompressible. And for solving the pressure, since pressure, actually solving this pressure is a set of linear system of equations. So each grid has pi grid. Each grid center has its pressure. So 100 and all those pressures are related to the surrounding pressure. So this is a huge system of linear equations that you would use Gauss Seidel method, which I'm sure you have studied in your numerical analysis course. And this is complete works. First we will choose the delta t, then we will advect the velocities, then advect the scalars, then apply the body forces, then we would compute the divergence, and then we would solve for the pressure, and then finally we would project such that the divergence, such that the velocity becomes divergent, and these are the key takeaways, and these are some references. Now I would like to show some simulations which I have recorded. This was one of the first simulations. This is actually completely unrelated to my other. This is actually a gas simulation using fixed pulse of initial. So basically, this is like a gas initially stored in a circular manner, and it diffuses out in a tube which has some oxygen and it completely spreads out. And this was one of my first top of the, I intended it to be a square of fluid falling down, but the top of the part somehow did not fall. So there was some work actually, some pressure followed, so that it did not cancel out the divergence. And this is one of the samples. So as you can see, there is some fluid falling down, and it's very compressible, right? And it also does not like fall on the floor, right? It does not bounce by falling on the floor. So many issues. Next one is slightly blue. So next one is slightly blue. So as you can see, the floor, after falling on the floor, the fluid slightly bounces. So I tried to implement the boundary conditions, but still there is some water loss in it. And this is one of the final solutions of the liquid part. So as you can see, there is some rectangular shape fluid. It's falling down, and it's like due to the water loss, actually it's disappearing. So here actually you can see the density is actually from 0 to 1. It holds values from 0 to 1. Either there is fluid or there is not. But if I change it to a continuous stage from 0 to 1, it becomes a gas kind of like simulation. So it turns out algebraic simulations are much better for like gases and all. As you can see. Yeah. So this is actually very satisfying to work. Another. Yeah. Thanks.
Hello everyone, my name is Dipash, and I would like to present my work on reinforcement learning for adaptive decision systems. Okay, so what is the problem? The problem is that dynamic environments demand adaptability. So as we can see that the real world is dynamic. There is nothing static. Everything is dynamic. The environment changes. So static rule-based approaches don't work anymore, right? And even machine learning, traditional machine learning models, they are also trained on static data. So when an environment changes with time, the machine learning models are also unable to adapt. So what is the solution? So our goal is to use reinforcement learning and create systems that adapt with the environment over time. So what is the difference between reinforcement learning and traditional machine learning algorithms? So the major difference are the data type. So in traditional machine learning algorithms, we use static data which is pre-collected, and in the case of reinforcement learning, we use dynamic data which is directly collected from the environment. Another major difference is feedback. So how machine learning, traditional machine learning algorithm models use, they use matrices such as mean squared error or accuracy, and in case of reinforcement learning, it uses a reward function and objective. So the major difference is also about how they optimize this. So in case of traditional machine learning algorithms, they try to minimize the errors, and in case of reinforcement learning, they try to maximize the reward that we gain. So how a reinforcement learning agent works, like how it trains itself. So you can see, first of all, there is a state. So what is a state? State is basically the observation that the agent collects from the environment. And after collecting the observation, the agent does the action based on its policy. The agent has some policies by collecting the observation, and using its policy, it takes some action. And from that action, whatever there is the changes in the environment, according to those changes, we give the agent a reward or a penalty. So using those rewards as a feedback signal, the agent improves its policies. So initially, when the agent doesn't have any policy, the agent does hit and try and does random actions to map out whatever the possible actions he can do and which action gives him a positive response. And after the initial policy is made, the agent does something called exploration versus exploitation. So in exploration, the agent still performs some random actions and try to find out more about the environment, and which action may lead to positive rewards. And exploitation. So with the random action, it also exploits the policy that it has already made. The agent obviously knows that okay, using these specific set of actions, I can get positive rewards. So if they exploit those policies to gain more and more rewards. So the two application projects which I have made in reinforcement learning are the first is pathfinding, the second is peer training. So the pathfinding. What is the problem with conventional pathfinding algorithms like A-star and Dijkstra? They use fixed maps, right? They use fixed cost functions and maps. So they don't account any dynamic factors that might be there during pathfinding. Dynamic factors such as that may be obstacle which is dynamic, that is moving obstacle or changing terrain. So the traditional algorithm doesn't account those things. How can we implement pathfinding? How can we implement reinforcement learning in pathfinding? So we can first create a state. So what are state might contain? So state may have a position, the correct position where the agent is, the obstacle location. So obviously the agent should know that where the obstacles are. It should have a complete overview of its environment in order to take action. So the terrain cone cost wherever the terrain is bad or good, and the recent path, because the agent may get over and over to the same path. So you must have data that okay, this was my previous path. And what might be an action space? So in a 2D world, in a 2D environment, the action space can be just discrete parameters that in which direction to move or not. And reward function. So in this case, we can create very basic reward parameters. They may be giving a huge positive reward if the agent reaches the destination, or a small negative reward if it hits an obstacle. And also another very good thing we can implement here is giving a constant negative reward each step. Why is that? Because when we give the agent a constant negative reward each step, then the agent will try to minimize the number of steps. So basically finding the most optimal targets. So here is the visualization. I have made the model and trained it. So green is the starting point and the red is the ending point. This is reinforcement learning in action. Okay, so my next project is related to a bit of finance. So I will tell a bit of finance. So basically, what is trading? You must all know that. Trading is just buying and selling of some assets and getting profit from the price changes. So there is a strategy in trading that is known as pair trading. So what basically pair trading happens is that we simultaneously trade two stocks that are correlated, and we use the mean revision properties of those stocks to get profits. So basic concept like what is going long or going short. So whenever you expect some price to go up, then you basically buy the stock that is going long. When you expect the price to go down, then you sell the stock basically going short. Okay, so in pair trading, you cannot directly select any random pairs, right? They have to be correlated in order to exploit the mean revision properties. So how do we select pairs? We select pairs using that spread, we calculate mean and standard deviation of that spread. And after calculating the mean and standard deviation, we can compute the Z score. And then how do we trade? So after we have the Z score, we have some fixed threshold value. That if the Z score goes above the fixed threshold, that is +2 and -2, basically we have these two thresholds. So whenever the Z score goes above +2, then we short it. Basically, we expect that the price will go down, and we short it. Basically, sell it. And if it goes below -2, then we go long, buy it. And when the price comes to near 0, we close long the trade. So here is the graph. You can see in the above image, you can see the orange and blue lines are the normalized price of the stock. You can see how both of them are correlated. They move up together and they move down together. But once you can see they diverge somewhere, there is a bit of spread made between those two, right? And when we calculate the spread and normalize it, the bottom graph, you can see that these are the thresholds, the long zone and the short zone, the two lines. So whenever it goes below the long zone, we long it, and whenever it goes above the short zone, we short it. So what is the problem with this method? So basically, this method relies on historical data. We calculate the spread on a rolling window of some previous data, right? So these historical relations might not hold during very volatile markets, and also we are using static thresholds. So they might not work during volatile markets. So how are we evaluating reinforcement learning in this problem? So basically, we can create a action space or observation space. What we need to include in the observation space? We need to include current position. That what is our current position? Are we shorting or are we long or we are doing nothing? Then we need to include spread, the normalized spread. That what is the current spread? Also the zone which we calculated previously, like the long zone or short zone. So why are we giving the zones again to the reinforcement learning agent? This is to speed up the learning process. Now the reward function. So reward function is basically a combination of reward obtained by trading and this is the cost per information. Like it is the transaction cost. So what the R agent tries to do is it tries to maximize the reward, and in order to maximize the reward, it does is it maximizes the profit gain and it minimizes the transaction cost. So basically maximizing the profit and minimizing the trades. Then the action space. So I implemented both type of action space in here. I implemented the discrete action space as well as the continuous action space. In discrete action space, we just get the reward signals, like either to long or to short. And in continuous action space, with the direction, we also get the quantity. So like if I get 0.2, then that means that I need to do 20% of my portfolio to the long, right? Now the experimental setup, what we used. So the symbols we used are BTC UR and BTC GBP. These are two cryptocurrencies which are correlated. You can see the correlation. Both of them tend to move together. And we have used data from October 23 to November 23 for the training purpose and December 23 for the testing purpose. So after training this RL, here are the performance of both of the models. So you can clearly see the one with the continuous action. He has performed significantly better than both of the methods, the traditional method as well as the discrete action space method. But one thing you can observe here is that the win-loss action ratio. So in the discrete action one, that is way higher than both of them. Why is that? Because in case of discrete action, you are giving action as +1 or -1, which is doing your good portfolio long or short. So what does the RL try to do there? The RL wants to play it safe. Because why? Because your good portfolio is going long or short, right? So he plays safe and does like more accurate, takes accurate trades, right? And in the case of RL2, he does a small trade, maybe whenever the agent is not confident, it can do a small quantity of here's the performance comparison of both of those models. On the left you can see the one with the discrete action, and on the right you can see the one with the reverse action. So the middle, the red part is the drawdown. So you can easily see in the discrete action and drawdown is very less. Why? Because again this is a very safe one, very safe. And in case of a continuous one, the drawdown is very much. So what are the challenges? When making reward signals, sometimes there may be some loopholes in the reward signal that the RL agent may exploit. So basically, the RL agent is not doing the work we intend to do. He just finds out a loophole and just exploit it to gain rewards. And again, extended training time, because RL requires significantly more training because it's learning from scratch basically. Future work that can be done here is real-time market data ingestion and low latency execution of the trade. These are the references and views. Okay, thank you.
So, hello everyone, my name is Yanshu Sharma and I am going to walk you through my project that is platform simulation using C++ and OpenGL. Okay, so let us start with a high level overview of the project. So, we are going to build a real-time simulation of our matrix-based superclassic platform that is hereditary HR, and the core technologies we are using to make this are C++ and OpenGL, and we will try to replicate the physics phenomena like gravitational density. Before going to the coding part, let us look at the physics of the black body. So, gravity is not simply a full force for massive bodies. Gravity actually curves the space-time around it. So, for example, if we see the space-time fabric around the black hole, we can imagine it by putting a very heavy ball on a trampoline, and then it will take a shape something like this. The main components here are the singularity, that is the point of infinite transdensity, and if we see the most important component for our simulation here, that is the event horizon. So event horizon is a theoretical boundary, and if we cross that boundary, the escape velocity exceeds the speed of light. Meaning, if light crosses the boundary, then it will not be able to come back. And the assumption that we are taking here for our simulation is that the black hole is non-spinning, and its radius is the Schwarzschild radius, and its formula is 2J by c square. So we do not actually see the black hole in the background. It is the image of the first black hole that was captured by NASA in 2020, and we do not see the black hole. We see the matter around it. These are the light rays, the particle, and the cloud that is present around the black hole. Now, for our simulation, we are simplifying our work only around the light path. So, in a normal space-time, light travels in straight line, but when the space-time is curved, light does not travel in straight line. It follows a unique path that is called the geodesic path, and it is the shortest possible path between 2 points. The general geodesic equation is something like this, and for our use, we use polar coordinates, and using those symbols, we solve this equation to get the acceleration equations, and we'll use these equations to update the position, velocity, the direction of the light ray, and its gravitational acceleration. Now the graphics engine that we are using is OpenGL, and OpenGL is a cross-platform API that is used to render 2D and 3D graphics, and it is widely calculate the path of the light in discrete steps. So the second thing is, if we in our simulation, if we keep a light, some light sources, and the light will originate from those sources, and then they will behave, react around the black hole. But the thing is that 99.99% of light rays do not enter our eyes. We only care about the light rays that enter our eyes. So if we take this model of putting light sources in our simulation, 99.99% of calculation we will be doing for the light rays which we will not see. So we need to optimize that, so we only do the calculations for those light rays which enter our eyes. And one more problem is using the Euler's integration. That is, it gives a very big problem that sometimes the light rays unnaturally bend and snap into the black hole without giving a perfect smooth curve. So what is our solution? The solution is backwards radiation and the strain point. So what we do is we map a 2D code that is a flat rectangle to the user's screen, and we cast rays from our eyes and then see the reaction of the light rays after their with the black hole, and then we paint the pixels according to how they behave in the black hole. So before going into the full 3D prototype, we built the 2D prototype to check whether the physical equation that we are applying gives us the perfect curves or the perfect direction of light or not. So this is the demonstration of the 2D prototype. So we can see some light rays escape and some enters into the black hole and some just orbits around it in the accretion disk. So now let us look at our engine and the computation that we are doing. So to get perfect curves for every ray, we need to do thousands of integration steps per frame to update the light rays and get perfect curves. And for every ray, for every frame, we update its velocity, acceleration, direction. So we require thousands of integration steps per frame. Now the problem that we discussed earlier about the inverse integration is solved by the RK4 integration method. And in this method, we calculate the slope between 2 points using 4 different components that are K1, K2, K3, K4, and the final updation rule is done by using this final formula. And let us look at the computation cost. So for a 800 by 600 screen, we have around 4,80,000 rays, and we need to do 20,000 steps per frame. And in those steps, every step is divided into 4 steps due to the RK4 method that we are using. So the total number of calculations roughly become 38 billion physics calculations per frame, and our CPU cannot process this workload in real time, and that's why we need to transition to our GPU for parallel computation. So how will our final computation pipeline will look like? The CPU will act as a manager. It initializes
So let's start with what is style transfer. In style transfer, we use two images, one as style image and a content image. We use this in a convolutional neural network in which we let the neural network learn the style of the style image and effectively give a stylized image of the content image. So, in the traditional NST or neural style transfer, the main problem is its risk. It is a optimization technique in which it iteratively changes the pixel values of the content image to change it. Like as you can see, this is the content image and this is style image. It will learn the style image first, and then iteratively change every pixel value of the content image as the first image and output the first image. It will take around minutes or even 10 minutes to give one picture, which is impossible for us to use in a real-time style transfer, in which we want around 10 to 15 FPS, like per second 10 frames should be stylized. So the solution is fast neural style transfer. In this, instead of optimizing each frame, we use pre-trained models. In our traditional NST, we don't use pre-trained models. We just use a neural network in which we let the neural network learn first the style and then change the content image. But in this, we have a pre-trained model on a specific style. So the model is trained on many huge data of particular style, and as soon as we put a content image, in our case, video from a webcam, it will stylize the image quickly and way more effectively. Also, by leveraging OpenCV optimized DNN module, which is deep neural network module, we achieve 15 to 30 FPS only using CPU, not even GPU. Let's go through the working of the system. Starting with the capture frame. First, we use our OpenCV module capture to get the frame picture, and then we pre-process the picture. So when we capture the image from our webcam, it's an image, and computers can't read image. It only reads maths. So we have to convert the image into maths. So we convert the image into 4D blocks, which is basically 4D array or tensors known as. So that the neural network can change the values of the block. And then after we convert the picture into 4D block, we pass it to the model that we want to change the style. And now it's a mathematical module, mathematical block. So we can't show mathematical block again to our human eyes. So now we have to change it back again to the image that we can process, and then finally display. So this is the core implementation, in our project. The main function we use in pre-processing is DNN.blob from image. So it just, as I said, converts the image into 4D blocks, which the computers can read and change value. It contains many values of different colors like RGB, the basic colors. So for every pixel we have a lot of different values of red, blue and green. So the only thing we have to change is the value, those values, to stylize the image. And after the pre-processing changing the image to log, we pass the matrix or block to our module, so that it can change its values and give a particular stylized block, and then that stylized block is part again. In this, a very important part is ImageNet.me. The values you can see 103.93 and 116. Those three values are the average RGB channels, which the original model was trained on. So, original model is trained on a major data set, and the new image is a different. So, we have to subtract these values from our new image so that the consistency of the module is maintained. But if we don't do this, we will expect raw pixel values, which will not it will not show the resemblance from the original image. And again, after pre-processing, we push it to the model and get the values changed, and then post-processing, in which we reshape the body block, which is 4-dimensional block of dimension 1, 3, h, w, where h and w are the height and width of the frame, to 3, h, w, where 3 represent the red, blue, and green channels. And as we subtracted the mean values, now we have to add again the mean values, so the resemblance from the original image is still there. So let's demonstrate first. As you can see, it's working pretty nicely. If we have used a traditional neural network, it would have taken around a minute to do each frame. But it is very responsive for now. And I've added some new features to it. When I press N, it changes the style. Again. For now, we can see it is giving around 50 to 30 FPS, which is pretty good for real time. And for currently, I have only put 4 styles: mosaic, Mutiny, and candy and styling nights. But we can put way more. And zero restart time means switching between styles is there's a zero lag between that. So these are the some of our achievements from our project. So for future enhancement, we can do one thing is called human body segmentation. So what I want to do is when there's in a frame, the human is there, only style will be transferred to the human figure. Rest of them will be same. So that is one of the aim, and we can even use DQ to make the performance better. And custom style training pipeline is also a big aim. Thank you.
Hi all, my name is Shortman and my project is realistic volumetric fog engine. So let's first understand the basic of OpenGL foundation. So the modern OpenGL serves as the rendering backbone for volumetric fog system. It uses shaders, models, textures for making realistic atmospheric effects. The VLSW is graphics language framework which creates window and for input operations. The GLAD manages the OpenGL functions, and JNF provides the mathematical formulation like for vectors, transformations. So the core libraries that are used in my projects are KSIP for model loading, STD image for image loading, and JNF, as I said earlier, is the mathematical functions library. So I have added camera and input system. So the camera is the first person view camera, which take data from your image, and there are mouse movement for camera rotation and key inputs for 360-degree freedom movement. So how this camera movement works? Firstly, calculate the angle set distance for your image data. Then from that we calculate these objectives, it gets scattered. And what this we use is any instant phase function. And after this, I applied exponential fog density, the y direction, and a radial density follows from the center. So the other new features that are dynamic sun animation. So the primary source of light, sun moves in a circular, like naturally only, and on the basis of the sun position, the color of the fog changes. The second one is runtime parameters, through which we can adjust the fog density, the surface count, and other parameters. The third is model and texture support, which occurs from the library which are imported, the STB image and the model input. And the third is bonding volume. So instead of using ray marking the whole 3D space, we are only implementing it in the specific cubic body where the object is imported. So we have also used pixeling for visual quality. Why it is important? As you see in this image, without it pixeling, there is a ripples in the retina, but after using it, it becomes smooth. So it reduces the banding, it makes the gradient smooth, it adds different noise, and it makes the fog look more natural and realistic. I've also integrated light and shadow. Firstly, we added directors and light from the natural source, which is the sun. Then we integrated the sun for shadow mapping, and using these two, we make a volumetric shadows. The first image shows the fog density map, and the second is the distance heat map, which is used to make the fog. So the advanced light techniques used as suggested is any instant function. So it uses the angle between the obstacle and the camera view, and using that it makes the light scatter so that what actually makes the heterogeneous atmospheric, so it make it look like the light which is coming from the sun, it gets scattered and then it is coming to the camera light. The real updates is because we are rerendering the shadow map, which ensures that the dynamic objects cast the accurate shadows randomly. So this is an example of the final output. The first is the model which I imported. The second is the fog map which is generated by the code, and the third is the fog model. So the references that I used for making the project is DMU research paper and a journal from CGT. That's all.
My name is Jasmine and my project is to accelerate learning propagation for large as well. So in this project I have implemented vector laws into aspect simulations. Now the motivation of this project was that most researchers who simulate solar systems, they find it difficult in simulating systems where a large number of celestial bodies are involved. In a typical solar system, we have thousands and millions of celestial bodies. So, traditionally, we use is mainly influenced by the gravitational influence of Sun. So their inter-asteroid interactions do not have a very heavy influence on their position or velocity. So we can reduce this problem of ON square to an ON problem if we consider only the gravitational influence of the Sun on every asteroid at any particular time. So this is what I have implemented in my research. So the main question is, can this simple maintain physical accuracy with respect to traditional methods? For the system architecture of this project, I've taken spatial horizons data as graphed here. Now this is a high precision ephemeris data from NASA. It has all the vital elements, parameters, velocity, and position at any particular time. And then the second layer is the rebound n body layer. It is a Python library which uses the traditional gravitational calculations to evaluate realistic orbital trajectories. It can also give us all the position and velocity of any particular asteroid in any particular direction at any particular time. So it uses the ON square complexity, and we compare it with our model, which is a layer 3. It is my model uses Kepler's laws. So it's a Kepler propagation model, which I have implemented using open and then we further do a error analysis comparing both the models. The orbital parameters can be used in my model. Some of these you might know from centimeter axis. Centimeter axis defines the height of the ellipse. Eccentricity basically orbit, inclination angle. It tells us how much the orbit is tilted with respect to the reference plane. Argument of peridian. It is the angle on the orbit where the closest point to the Sun lies for the body. Longitude of ascending node. Same the angle adjusts the horizontal orientation of the orbital plane lies. And then finally the mean anomaly. It's the angle on the orbit where the asteroid actually is along its orbit. So basic orbital mechanics formulas before we dive into the algorithm. Peridian distance, closest distance to the Sun, then farthest distance to the Sun. Orbital period using Kepler's law. And then for using calculation, we take 1 by e plus c by 2. Here is the distance. Then the Kepler propagation algorithm. So we calculate the mean motion, which is k by 1.5. Here is the Gaussian gravitational constant. So the mean motion tells us how fast the asteroid is around the orbit. Then we update our mean anomaly, and not just the mean anomaly at the approach, and then we update it using n, and then we take the Kepler equations. This is the standard Kepler equation which relates mean anomaly and eccentric anomaly. But this is not directly solvable, so we use the Newton-Raphson iterative method to solve it. In my model, I've performed this algorithm 20 times to finally convert the value to E, which is the eccentric anomaly, which we will read later. So the final orbital mechanics formula, using E we get the orbital plane coordinates of the asteroid. basically transformation and the transformation formulas. And the final position vector is R XYZ. So the demonstration. So we implemented all these equations, and also we have a visualization made on OpenGL. So these are basically 1.5 lakh asteroids in the system. The colored spheres are the planets. We simulated these. So these are being simulated frame by frame. This is a speed up demonstration. So these are being simulated frame by frame, and these are all asteroids. You can see the asteroid belt. We know the asteroid belt that basically lies between Mars and Jupiter, so it's a demonstration of that. These are being simulated frame by frame. The final physical validation of our model. So we evaluate the model on 100 asteroids for a 1 period time frame to check the error presence with it with the traditional model. So the error was found to be 0.017%, which is negligible. And then to find unusual differences, we also did a threshold analogy correction. Using that, we found that most of the error was found mostly in the velocity, if there was mostly in the velocity, and it basically explains that even if you reduce the OS problem to a OS problem using Kepler's law, the errors for the position is very negligible, and this shows a very stable behavior. Explains that a model is physically consistent with the n-body simulation for short-term asteroid configuration. Further, we did a long-term stability test, which was a 20-year test. So we evaluated 100 asteroids for a period of over 20 years to see if there is any divergence that occurs between the models, and the divergence was found to be around 10 to the power -6 astronomical units, which is also very negligible. So very few anomalies, and most divergence were velocity dominated. So meaning the differences occur mainly in velocity and large position errors. This is a C2 scalability study. So we evaluated a model on C2 and these are the results. So for 100 asteroids, you can see the CPU was on CPU we got 12.5 seconds to milliseconds to run the model, and on GPU it was 0.01 milliseconds, which was 1200 times faster. And as we increase the number of asteroids, the CPU is able to take the computation faster and faster with comparison with the CPU. This resulted that our model is able to do 357 million propagations per second. We did that for 15 lakh plus asteroids in this research. These are some references that we used for this project to get the data set and all the equations. Radial horizon, city bound, and Kepler's equations, and then the MPCOL database for getting the parameters for 10 lakh asteroids. Thank you.
evening everyone. Today I am presenting later open field place fiber farming. I open field development remains challenging. I open field has been around for 3 years. Developers face several common challenges. First, complex capability, create windows, initialize OpenGL, text and code extensions, requires platform and we also need to manage the configurations for different versus Windows, Mac OS, Linux, and we need full maintenance for GLW, GLAD, GLM, and products. And we also have to validate copy of our project. This system architecture for the project we use the template to create two projects. We don't need to compile the program again. They shortcut for the shaders. And the sources, that is textures, meshes, shader assets are just with the library for generally. The first application is the simulation. As you can see the example, it generates symbols and we can even see interference create multiple images at the same time. The parameters and the height of the speed is the person in case A, then number of people can create frequency and speed. For example, if you change the case A, the person moves quite fast. It is a GPU based simulation so that yes, that's interactive because that's factors for every parameter, and we can read it to see simultaneous. The data pipeline technically uses a two-pass pipeline simulation. The fragments get a computer flashing, and then the chromatic shader supplies to the image. The performance metrics runs on CFPS using a limit on medium level GPUs. Second is a old gel, that is a protein structure engine. We can utilize this we can move around just look around the beam. Model and the backbone. Also, can be from CGS. Okay, fine. ठीक है, तुम लोगों को कुछ क्वेश्चन पूछना है?
How do you guys choose your projects?
Maybe we first of all give you a couple of projects on which you can work on, and based on that, what interest you can choose. Like best thing is to just learn read the papers and you revise that by yourself. Like pick some topics, just search some random YouTube videos, learn about it, and then take simulation and whatever you want to do. Any other questions? Yeah, so basically, currently, during April, we'll be having two sessions regarding R&D posting, and later in summer, we'll be giving you projects for R&D, and we'll be having a lot of projects, and based on that, you can choose some projects and talk to us regarding what project you want to work on, and we'll give you insight and you can go for that, and based on what your project turns out, if it's good, we'll take it to R&D.